Welcome to this presentation of the VM80 and VM100 vibration analyzers. In this video, we will show you the frequency analysis functions of the instruments. The frequency analysis module is included in the scope of delivery. It supports 3 measure-em channels. The vibration analyzers are simple and intuitive to operate via touch screen. There is a multitude of applications, for example, in predictive maintenance for the early detection of machine damage by bearings, gearboxes, or unbalances, in research and development, like structural analysis or NVH tests, and in quality control and condition monitoring in areas such as vehicle manufacturing, aerospace, wind power, and construction, to prevent failures, increase efficiency, and ensure safety. First, let's take a look at the settings menu. The device offers various analysis methods. FFT, or Fast Fourier Transform, is an algorithm that computes the discrete Fourier transform of a sequence of signal samples. A Fourier transform converts the signal from its original time domain to a representation in the frequency domain. The result is a spectrum that shows the distribution of frequencies over a selectable range. FFT can be measured not only with accelerometers, but also with sensors for force, pressure, or sound pressure. The FFT of velocity is reserved for accelerometers. It calculates the integrated spectrum. PSD, or Power Spectral Density, is the measure of signal's power content versus frequency. Unlike the FFT, the amplitude of the PSD is normalized by the frequency resolution of the spectrum, which is the size of the discrete frequency bands. PSD is often used to characterize broadband random signals. It is less suitable for stationary sine wave signals. For vibration data, a PSD has amplitude units of meters per second squared per hertz. Similarly, ESD, or Energy Spectral Density, represents the distribution of energy in frequency domain. The result is also normalized by the frequency resolution. ESD is the measuring unit meters per second squared times seconds per hertz. FRF, or frequency response function, characterizes the response of a mechanical system by exciting it with a force pulse, in many cases by an impact hammer. FRF reveals natural frequencies and mode shapes. You can choose between the calculation in units of acceleration, velocity, or displacement, per newton, or the inverse. The amplitude axis can be linear or logarithmic. You can choose between RMS or peak spectrum. Windowing is used to reduce the effects of spectral leakage. Spectral leakage refers to the blurring of the signal from one frequency interval into neighboring ones. Each of the different window functions has pros and cons in terms of amplitude accuracy and frequency resolution. The hand window is a good compromise for many applications. Hamming allows sharper separation of closely spaced frequencies. Flat top is used when high amplitude accuracy is required. The rectangular or uniform window is essentially applying no window, giving all time samples equal weight, which offers the best frequency resolution but causes severe spectral leakage. For time-varying signals, several spectra can be averaged before display. With the hold maximum function, the highest amplitudes, measured since the last reset, remain visible in the diagram. The calculation of spectra can be triggered in different ways. Auto measures the next spectrum as soon as the previous one has been finished. Analysis can also be triggered by an impulse at the RPM sensor input. With amplitude trigger, a new spectrum is measured as soon as a sample exceeds the entered limit. With single amplitude trigger, a single spectrum is displayed when a sample exceeds the limit. Reset must be pressed for reactivating the trigger again. The signal bandwidth can be 4.4 or 22 kHz. It determines the frequency resolution and the calculation time per spectrum. In FRF mode, the bandwidth is fixed at 4.4 kHz. The gain can be set individually for each of the 3 channels. For periodic signals, auto-ranging is recommended. For highly fluctuating amplitudes, a fixed gain may be better. Channels can also be switched off. In waterfall mode, up to 50 previous spectra are displayed in the background of the currently measured spectrum in pseudo-3D style. This can be useful, for example, to make resonances visible during run-up or coast-down tests. In spectrogram mode, each pixel line represents a spectrum. Amplitudes are color-coded. The highest amplitudes are red, the lowest black. In the upper part of the screen, you can see a color scale labeled with the amplitudes. Up to 340 spectra can be displayed. Waterfall and spectrogram mode support only one channel. Let's now take a look at the spectrum display. The spectrum diagram occupies the entire screen width to enable maximum resolution. At the upper edge, you will find the 3 broadband RMS or peak values measured in time domain. The line below shows the selected settings. The amplitude axis, which is scaled linearly or logarithmically depending on the setting, can be changed using the plus/minus buttons. The auto-scale button does this automatically according to the largest spectral line. There are also buttons for zooming in and out on the frequency axis. The scroll bar is used to select the frequency section. There are 2 cursors that can be used to examine the spectrum. They can be moved by touching the lower end. The cursor buttons on the left and right can be used for fine positioning. The 3 amplitude values and the frequencies are displayed for both cursors. Cursor 1 also shows the frequency difference. Touching the RMS between cursors button opens a window with the 3 RMS values of the spectrum between the 2 cursor frequencies. This is a convenient method for selecting a frequency range and determining the signal portion within it. The maximum button displays a window showing the 6 largest amplitudes and their frequencies for the 3 channels. The output of the spectra can be stopped, in which case the last spectrum is retained. Finally, we will look at the measurement of a frequency response function. An accelerometer is attached to the test object. An impact hammer is used to strike the object in order to test it for resonance frequencies. It applies a known force impulse to the object. The impact hammer is equipped with a force transducer to measure the applied force. This force transducer is connected to channel 1 of the analyzer. The FRF measurement is triggered by an amplitude trigger. To determine the trigger threshold, the settings menu provides the signal shape of the force impulse. In this case, the amplitude is approximately 50 Newton. We set the trigger threshold to 20 Newton. After closing the menu, we begin with the actual measurement. Before taking a measurement, always press Reset to establish defined start conditions. Then we apply the first force impulse. The green trace shows the impulse response spectrum of the object. In this case, we can see resonances at 2 and 2.9 kHz. The orange trace shows the spectrum of the force impulse. It should be as flat as possible in the range to be examined in order to excite the entire spectrum evenly. Since 3 channels are available, the spectrum of a second accelerometer could be measured additionally. To save measurements, press the Save button. Spectra can be stored on the device's SD card as a bitmap screenshot or as a CSV measurement table. The suggested file name consisting of date and time can be changed if necessary. The analyzer has a read function for NFC tags to identify measurement points. These contain a unique identifier that can be linked to a descriptive text. In this example, we save the measurement as a CSV file. It contains a header with data on the measuring device and the connected sensors, as well as the settings for frequency analysis. The actual measurement data, each point consisting of frequency and 3 amplitudes, begins in line 22.